So, like we said, we started with Newtonian, we started with Lagrangian, and today we're going to talk about Hamiltonian. Before I go into this, there are two small things that we need to talk about, okay? And I will probably get into the details of this again later once I get into quantum mechanics, but let me just tell you a couple of things which are kind of important. One, see, if you take an equation of this form, let us say LU equals 0, right? I take an equation of this form, where L I'm calling is some linear operator. I'm calling L some linear operator. U is some equation of a dynamical system, whether it is, something like d2x, the second derivative of position with respect to time is acceleration, right? Something like that. So U is something like x, or U is something, and L is some operator, like your derivative or whatever. So this is some observable, something which can be observed, some observable in our language, right? It can be momentum, it can be weight, it can be position, it can be velocity, it can be anything. It can be something that you can measure, anything that you can measure, right? That is U. L is some linear operator. Okay. LU equals 0, and then you are trying to find, of course, the solution to such a problem, right? You're trying to find the solution for such a problem, all the different values that satisfy something like this. Now, there's a lot of confusion on this, and that's what I wanted to talk about before I get into Hamiltonian. What do I mean when I say L is linear? Okay, I said L is linear, right? And I made this statement. Now, for example, L can be anything, right? L can be a derivative, L can be some sine or cos, L can be whatever, some polynomial function. L can be anything, some operator on an observable. That is what this is. And I'm saying L is linear. When I say L is linear, what do I actually mean? Anybody has a clue? What does that mean? This can be anything, right? For example, given I can say, I don't know, d2x by dx square plus some 1 by tau sine x equals 0, something like that. It can be anything, right? Some operator where sine and d2x. So some operator, and I'm claiming when I write this like this, and when I claim that L is linear, what do I mean by that? Okay. Because I think there's a lot of confusion among linear and non-linear operators. People keep getting confused. So, okay, I won't waste a lot of time because I think we're short of time. When I say L is linear, it has to satisfy two conditions. Yeah. Two conditions, two simple conditions. Given LU equals 0, alpha of LU implies alpha LU. Very clear? So if I'm multiplying it where? Alpha belongs to some real number. Alpha is some real number. Okay. If this is satisfied, if this condition is satisfied, simple condition, where if I'm multiplying, then it just means multiplying the operator by that real number, and then putting it on top of, and you can see for yourself that the derivatives are linear operators. You can check that, right? Dx square. Now, if I say ddx of 3x square, that is 3 ddx of simple condition. We will see cases where this is also not true, but for now, let's just imagine this. And second condition, is given LU equals 0. If I say alpha plus beta, LU is alpha LU plus beta LU. If I can write it like this. Okay, then this equals 0 and all of that. Actually, that also means if some alpha and beta are roots of this, anyway, let's not get in there. But is this condition clear? You're just opening it, associative property, right? That's all.
Yes.
So if these two conditions are true for an operator, it is called a linear operator. And it is a necessary and a sufficient condition. If these two conditions are there, it also means it's a linear operator. So both ways it's true. If it's a linear operator, it implies these conditions. If these conditions are true, it's a linear operator. Okay, it's very simple. We'll not get into too much detail about this right now. But there will be a class in quantum mechanics where I'll get into some depth on why this is very important. Now, the operator that we will see in Hamiltonian mechanics. See, and one more thing you should understand as you're getting into quantum mechanics and all of that. Usually, when I say Newtonian mechanics or Lagrangian mechanics or Hamiltonian mechanics or quantum mechanics, these are frameworks. Because I think there is confusion. When you think about mechanics, you will largely, a lot of people will think it's about balls rolling on the floor or something sliding on, inclined planes. That is all mechanics, and something is electricity, something is light, and that's kind of the way they teach you physics, unfortunately, in most schools. But when you really talk about these things, these are just frameworks. Newtonian mechanics is a framework where you talk about forces. Okay. Now that can be applied to electricity, that can be applied to light, that can also be applied to mechanical movements. But Newtonian mechanics is a framework. Similarly, Lagrangian mechanics is a framework where you're trying to get to the total energy and then you're trying to minimize the energy across a path. Okay, and you're saying that's the path the particle takes. Okay, so that is a framework. Now you can apply that framework to any part of physical phenomena that you see. Okay. Similarly, Hamiltonian mechanics is also a framework of looking at the world. Think about these as different lenses. You can use different lenses to look at the same thing. Okay, so the physical reality is the same. The lens differs. What lens you put on to see. Okay, so if you think like that, it kind of makes quantum mechanics is one more framework. Okay, it is another framework to look at reality. Right? These are all different lenses to look at reality. The way the human progress has happened is it happened in some chronology, but that doesn't mean it is chronological. They are just different lenses, and different lenses make sense at different times. Right? For example, I may have long sight as well as short sight. So when I'm reading something close, I will put the short sight lens. When I'm looking at something far away, I'll put the long sight lens. It's not like one is better than the other. They are different lenses to look at the reality that you need to look at. So similarly, Newtonian mechanics makes sense in certain questions and quantum mechanics makes sense in different questions. Okay, so the reason I've said this is because a lot of people have a feeling that somehow this is superior to that or that is inferior to that. That is a very wrong way of looking at it. Okay. And Hamiltonian operator, we will see at the end of this. I'll probably leave it as a homework after I explain Hamiltonian mechanics to you. Is a linear operator. The Hamiltonian operator is a linear operator. And strangely enough, even though all of you may think so, Newtonian mechanics is actually non-linear. In your home, go and try this. And next class, I will tell you why Newtonian mechanics. So actually, it's very strange. Quantum mechanics is actually linear and classical mechanics is actually non-linear. Okay, and we all think somehow quantum mechanics is far more complex. Mathematically, it isn't complex. It's actually sort of a little bit easier. Unfortunately, they make you solve those problems for IIT. They will probably make you solve these problems. These are actually easier to solve rather than. Actually, you will see if you actually study first year engineering properly, you will see that most of the problems that you struggled during your 12th class, if you just use Lagrangian equations, they become trivial. You can just solve them just like that. Unfortunately, they'll teach that in first year of engineering. They will not teach you in 12th class. Maybe it is sadism, I don't know, whatever it is. Anyway, so now that you have got here, now there is one equation we need to start, and from that we will actually get into Hamiltonian. Schrodinger's equation. Has everybody heard about this guy?
Yes.
Yes. Schrodinger's equation. The famous cat nonsense. Right? Everybody heard Schrodinger's cat and I were dead and things like that. Right? I will not get into that. If you haven't tried to read any popular science thing. So what is Schrodinger's equation? It is the equation for a dynamic quantum mechanical system. Like, for example, what you write, right? So for example, what do you say? You write mass into d2x by dx square equals v dot, right? The first derivative of the potential with respect to dt. V dt. V being the potential, V being the potential. This is Newton's first law, second law, right? Force equals mass into acceleration. This is force and this is acceleration. This is ma and this is force. Force is the first derivative of the potential with respect to time. So this is Newton's second law, right? So similarly, so for example, classical mechanics, you have Newton's law. Here you have Schrodinger's equation. Okay, and why I'm writing this equation is just to tell you why Hamiltonian is important. Now I'm going to write an equation. Don't get frightened by it. Okay. This is why we spend complex numbers, time with complex numbers, because now in Schrodinger's equation, complex numbers is not a mathematical trick. In classical mechanics, in Maxwell's equation in electricity or wherever, you use this as to simplify equations. Here it is not simplification. This is the equation. It is a very part of the equation for the quantum dynamical system. This is h bar. This is known as Planck's constant. We'll talk about it when I get to quantum mechanics a little bit. But right now, don't worry about it. Partial derivative of psi. And I will explain what psi is. So this is what it is. If psi gives you, if psi is a function of the position of an electron with respect to time, then you need to understand how it changes. Right? So that is what the dynamical equation is. Right? It explains how an electron moves through time. Okay? So the first partial derivative, it's a partial derivative because it depends on a whole other host of things, which we will just forget about it for now. There's a whole lot of nonsense that we'll get to when we get to quantum mechanics. But this is equal to, now here is where, don't worry about this, we will simplify the whole thing. This is called Schrodinger's time-dependent equation. This is the name. Okay. So now you can tell people you have at least seen this. We will get into this over the next few classes. But now, what do we do? This whole thing is called the Hamiltonian operator H. Okay. So it just becomes equals to Hamiltonian plus something. Okay, where V of x is also always the potential. When I say potential, it is the energy of a particle because of where it is. Okay? It is some potential of the, and here we are thinking that the potential is kind of somehow dependent on x in a lot of times, and you can have multiple Schrodinger's equation because this is on displacement itself, but a photon has also a spin. not just position. So even if it's at rest, it has some potential. So things like that, you can have multiple Schrodinger's equation. Instead of x here, you can have spin with respect to time, and then you can measure. That's one more Schrodinger. You have to solve multiple Schrodinger's equations to get to understanding where a particle is, and we will derive the uncertainty principle and things like that from this equation later on. But that's fine, right? So at least at a conceptual level, now you know why you need to get to Hamiltonian. This is what is called the Hamiltonian, which we will try and understand a little bit. Okay, we will understand it in the classical world first. Okay, then in the quantum world, we will change that, but it will be the same thing. At least conceptually, it doesn't change. So till now, you're largely fine with it, guys?
Yes, Srini.
So the equation, but it was told that it won't come to the exam because nobody understands this. Nobody can explain or read.
Oh, no, you will understand. I will make sure you learn. It's not so difficult, okay? I don't know why people do all this drama. It is not so difficult, actually. Okay, it's a pretty simple equation only. See, this term, if you really conceptually think about it, you are saying the first derivative of something depends on the second derivative plus potential.
Yeah.
Okay, that is what you are kind of telling me here. Okay, conceptually, what does it mean? It means how fast a particle is moving at a point is somehow dependent to how fast it is going to accelerate at that point, plus some potential of that particle at that point. That is what you're trying to kind of say. Now, in fact, if you are really clever, you can deduce uncertainty principle right from here conceptually. But let's not get there. I will not. That took a Heisenberg to do that. You and me are not Heisenbergs, so we will not be able to do it. But we will derive it. Okay, you can derive it. It's not so very difficult. Okay, so now we will get to proper Hamiltonian equations, and I will write them in the classical form, and then we'll explain what that classical form means. Before that, maybe I should talk about. Are you guys familiar with what is curl and divergence? Okay.
Not curl.
Curl and divergence. Let's quickly take 10 minutes and talk about curl and divergence. These are mathematical concepts.
And in the previous equation, if I'm just imagining a car, it is making much sense. Like from here to here, how speed or it is.
Correct. Is how fast it is going to be moving here plus that. But the problem in the quantum mechanical system that we will see is in a quantum mechanical system, the concept of position is very different than the concept of position in the classical world. And we will see another experiment when I get there. We'll talk about another experiment which will make that clear and why this world is as confusing as it is. But let's do this. Then I'll talk about, you reminded me, remind me at the end, I'll talk about a nice experiment on the photoelectric effect by Einstein, which will actually tell you what you're talking about. Okay. Anyway, curl and divergence. What is curl and divergence? See, think about anything, right? Think about a vector field. When you think about a vector field, what do you think? You think about different magnitudes, right? Different things moving here and there. Each one of them is a vector. It's a vector field, some vector field, okay? In some two-dimensional space. Each one of them is a vector because it's got a direction and a magnitude. Okay, that is all that there is. So this is a vector field. Now, what is curl and what is divergence? If you really take some sort of fluid under pressure, think about it. If you actually have some fluid, and I'm going to be, I'm not going to spend too much time on this because this is just some basic concept you need to understand for me to go into Hamiltonian. So you're just going to be, if you're putting some fluid under pressure, under a motor or a pump, it is flowing and things like that. You will see some parts of the fluid where all fluid seems to be going out. Then in some areas you will see that things are coming in, right?
Different fluids or the same fluid?
Say same fluid under pressure. No, if water is generally flowing, you will not see this. But let us say sometimes you would see, you open the sink hole and you fill up the sink. It will start kind of forming a tornado type shape. At some points, you will see that water is all flowing to one. point, okay? Some points you will see that the water is, if you have multiple sinks, let's say water is flowing and you opened multiple sinks one after another, you will see some such behavior of a fluid. When it's under some force, either some pump is pumping it or something is pulling it or something like that. Have you seen this phenomenon?
Yes.
Okay, with what? You'll even see it with, if you really boil milk a lot, khova, if you're trying to boil it like khova, farming. Okay, when the molecular movement becomes very high, the temperature becomes very, very high of some fluids. Most fluids are not incompressible, unfortunately, but that's an assumption we make. But anyway, have you seen this sort of phenomenon in fluids? Typically, you can see it in fluids. You can see it in everything. You can see it in air, gas, everything. But fluids is easy to visualize. Guys on the phone, do you kind of see this sort of thing?
Yes, Srini.
It's not a very difficult thing. Most people would have seen this. Paal Pongichra, you'll see that. Where if you go beyond a certain point. So divergence is kind of defined as the amount of something flowing out. So divergence at this point, if you look at if divergence of F, if you say F is at that point, okay, is the total amount of fluid that's going out. So it's basically how much is coming in. See, if you see it like, you can think about this like some pseudo source, right? It is as if there is some source here, and here you can think as if there is some sink. Something is pulling. There's actually nothing, but the fluid behaves like that. Okay, as if there is something that is as if there is some source of the fluid here. So divergence conceptually can be simply defined as fluid flowing out. So if divergence is greater than 0, that means more is going out. If divergence is less than 0, it means here it will be less than 0. Right? And when there is no divergence, 0 means same amount is flowing in as it's flowing out. That is all. That's all you have to kind of understand as far as divergence goes. At any point, divergence is the amount of fluid that's kind of going out from that point.
And at the point or a of pressure or pressure?
No, wherever you are calculating.
Okay,
Wherever you are calculating, and that's why at most points it will be 0. Okay. In fact, if there is no force, see, that is the way to say, if you have water flowing calmly under no force, no wind, no nothing, and if you assume water as incompressible, then the divergence of water flow is 0. Water will flow at equal pace. Okay, the divergence of F everywhere in that field. And see, and this is known as phase space. Okay, there's a word that we use. Phase space is nothing but a vector space. Is another word for vector space. That part of vector space that we are interested in analyzing is called the phase space. Because this whole thing, the whole universe can be a vector space. But within that, what parts of that vector space do you want to analyze? Because I'll be using this terminology a lot. I'll say there is a phase space. The divergence of this phase space is 0. Okay? Or the divergence is non-zero or whatever we say. Okay? So this is divergence. Now, what is curl? Very quickly, I'm just trying to do it very, very quickly. Curl is the rotation. Okay. So if there is divergence, you think about it. If you put a twig there, it will rotate, no? In any place where divergence is greater than 0, if you put something, it will actually rotate. The rotation can either happen in a clockwise direction or in an anti-clockwise direction. Correct? It's either clockwise direction or anti-clockwise direction. Based on how the divergence is there, right? So that's how it is. So when it is clockwise, by convention, when it is clockwise, we say curl greater than 0. And when it is curl less than 0. Okay, this is just convention. There is no real reason why anti-clockwise has to be negative and clockwise is but it's not some guy, it's again Gauss who kind of did this, and Gauss basically decided this is how he will calculate curl. It's a very, very interesting concept. It is used a lot, especially if you are into aeronautical engineering and things like that. All that you do, maybe you guys have heard something called finite element analysis. I don't know if you heard it or not. FEA, finite element analysis. Anybody here has done masters after mechanical or something? Would have probably heard that. Maybe in bachelor's.
Yeah, I have heard finite element methods, FEM.
Exactly. So finite element analysis is essentially this. Calculating so that how much lift is there on the aircraft wing, this. You know, the most complex thing you can ever think about in this field to analyze, all of you have access to that. It's a Pringle chip. Have you ever seen the shape of a Pringle chip?
No, slightly.
It is called an hyperbolic parabola. Okay, it's a very fascinating shape. Okay, that shape was created by the man to maximize the surface area to human taste buds. And the point where the saltiness of the human tongue is highest, it maximizes that. That's why you can never eat one Pringle. You eat one, you eat another one. It is actually a brilliant engineering design. Okay, absolutely brilliant design. Nobody remembers, unfortunately. And if you actually analyze the airflow on a Pringle chip, you can do one of the best understanding of curl and divergence in your life. Anyway, so sorry for digression, but that's fine. Okay. Now, how do we calculate it? Calculation is very simple. Okay. And again, divergence at F is basically your dot product, and curl is basically your cross product. Why? It's again very, very simple. It is dot product because it gives you similarity, right? So if you have divergence, everything, for example, if you have curl, everything is coming like this. So if you calculate the dot product at that point, it will become negative. The reason it will become negative is everything is coming to the center. No, so if you're taking a dot product is what? The similarity between these two vectors. So it will, if it is this way, it will become negative, and if it's the other way, if it's going out, it will become positive. So that is why this is defined as the dot product operator. This is known as the linear operator, the divergence operator into force, into the vector. And the curl is the dot product because curl is perpendicularity. Two things are perfectly perpendicular like this, it will flow like this. If it is like this, it will flow the other side. So that is what it is. This is defined as the cross product or the dot product because cross product measures how the orthogonality of two vectors. Right? The orthogonality of two vectors is measured by the cross product of two vectors. So that's how it's defined. There is nothing very great. Just one thing you may want to kind of see. I want to talk about this briefly. Again, this is one example for you to go home and do some study if you haven't done. People remember Maxwell's equations? Maxwell's electromagnetic. Okay, so don't worry about this, but you should probably know this because this is divergence of an electric field is rho by epsilon 0, where rho is the resistance of the medium divided by the electric field, by the intensity, is the divergence. And then the divergence of the magnetic field is always 0. This is probably the law which makes it possible for you and me to have cell phones. If this was not 0, then you will not get it. Why? I'll tell you. Then this is curl of the electric field. Curl of the electric field is minus in the opposite direction of the magnetic field with respect to time. And curl of B, which is the curl of the magnetic field, which direction does is mu 0, this is J, the electric current flowing through it, plus dE by dt, which is the change. Okay, so anyway, so the thing to understand this is what does all of this tell you? You don't have to go into this, go and revise your 12th class electricity things, Maxwell's equations. But Maxwell's equations are all linear. And number two thing, the most important thing is, you guys remember the right hand, left hand law? Right? Electricity flows in this direction, flows in this direction, then this is the flux. Remember that, right? I think Raju left probably. So essentially what happens is, why does this work? See, think about it. Yeah. in your cable or in your medium, there are so many conversations that are going on in parallel at the same time. They don't interfere with each other. Otherwise, even in air, I am talking to you, there two people could be talking, there two people could be talking, and still you can, to a large extent, make out who is talking to who. It can get completely mixed up in the medium, right? It does not. Electromagnetic radiation, it doesn't mix up because the divergence is zero. It is incompressible. Okay, it is one of the greatest gifts of God to humankind that our atmosphere is such. If it was not such, then we could have done anything. Nothing is possible. I couldn't even talk to you. I couldn't talk to you because then I will go all over. But it doesn't. Electromagnetic radiation is, the divergence of the magnetic field is zero. Anyway, I don't want to get too much into that. Let us get to Hamiltonian now. All right, so you guys have a basic understanding of curl and divergence now? Okay, good. Hey, I'm just moving on a little fast. So guys, tell me if you want me to slow down, I will slow down, but that is what it is. So Hamiltonian mechanics, you need to understand two equations and we will get into them. Okay. One is dx by dt equals, and don't worry if you don't understand them, we will get into this. And dp by dt s of p x. We will see what s of x is. What is. See, x is position and p is momentum. What is momentum? Mass into acceleration. Mass into velocity. Sorry. Mass into velocity is the momentum, right? So x is the position, p is the. These are known as the Hamiltonian equations. Okay, where Sx is defined as and Sp, that H is the Hamiltonian. We'll have a minus sign. Okay, and we will see what that Hamiltonian is. And these are the Hamiltonian equations that you have to kind of not remember, but at least understand. And we will talk about this a little bit in a little bit of detail. Now let us draw this curve and try and understand this. This is important. Let us say you have something like this, where this is x, this is p. And let us say you have some vector field like this. Yeah, drawing this is difficult. I will try, but vector field is always tangential, right? So it's always going to be tangential to the force. So it is some force field like this. It can be any force field, right? It can be an electricity field, it can be a magnetic field, it can be anything. So you can think about this force field as the vector xp. This is what when I said S is nothing but this phase surface, this phase field, this phase space of some force field called S, okay, which is like this, which is nothing but S of x comma S of p, right? For each thing you can have an p component and an x component for each of these vectors. So this is what this is. Now you think about this. How will this particle move? If you draw the trajectory of this particle under a force like this, it will move like this, right? Because this is what is the force field. So it will actually move like this. Now what does this mean? So it moves tangential to the application. So the force is applied. So here the force is where it moves along the vector. So how does the particle move is nothing but a derivative of the force field. Because however this force field is moving in time, the particle is also moving exactly like that. So it is nothing. It is. So this can be written as this S of xp can be written as just ddx, right? Of ddx of, in fact, maybe it is easier to write it like this. Differential of time with respect to x of t and p of t. So you have x of t, you have p of t. That is this vector field. Okay. Then you differentiate it with respect to time, you get this force field, you get the S, right? You just do that. So which is nothing but your S vector. Up till now is clear?
Yes.
So now, what is Hamiltonian in this, right? So let us get to the next part to get to Hamiltonian. So it's nothing. You have a force field, a particle moves along the force field, so you can talk about the first order derivative of it to be the motion of the particle under that force field. Okay, that's all that I'm saying here. Now we'll get to what is an Hamiltonian. Time, and then what is the time?
40.
I have to stop it. Now let's again draw this so that I can draw this in a little more clearer way. Let us say you have some 3 or 4 force fields like this, right? And let's in this case say forces are traveling like this all here. And then simultaneously everywhere. Now this can be each one of these curves in your phase space, which is basically your surface curve in your phase space, can be taken as an Hamiltonian at a given energy level. That is how you define it. So for example, this is h equals k0, let us say, some energy level k0. This is h equals k1. This is h equals k2. At different energy levels, let us say the forces are like this, and hence the particle moves along this. So this path is known as the Hamiltonian. This surface curve in a phase space. So this is the whole phase space, right? Where you have all sorts of vectors in there. And this phase space, now if you draw the vectors, they'll probably be, because they all have to be tangential. So it'll all be like this. Okay, something. And again, maybe this will be a little bit more straighter. And this will be even more like that, right? So there's a whole tangential, and then once you come down, it will be in the opposite direction, right? It'll get to be like this. Because the movement has to be tangential, tangent to that, tangent to that, tangent to that. So that's what. So this is how So this is how you kind of define your Hamiltonian. Hamiltonian is given a phase space. The surface curve at a given energy level is known as the Hamiltonian for that energy level. Okay, so this is the Hamiltonian. So this is the Hamiltonian operator. So if you apply an Hamiltonian operator, you will make the particle move like this. You apply the Hamiltonian at this energy level, you will move it like this. This is how the Hamiltonian is defined. The Hamiltonian is just defined as that trajectory in the phase space which the particle will take at a given energy level. That is what it is. Okay, nothing more complex than that. Mathematically, it gets a little more complex, but we don't have to first understand it conceptually. This is all the definition of Hamiltonian is. Okay. Now, why is it very, very important? It is we will see it is very, very important because it makes no assumptions about anything. It just says any vector field if there is a field of vectors in which or the motion is orthogonal, at every point it is tangential, then you can understand where the particle will go next. Depending on that initial condition of that energy level, if you know, you can draw out the entire trajectory. You don't need to know anything else. It makes no assumptions about linearity of anything. Okay, about anything being linear, forces acting, not acting, what force are there, don't care. You have a vector field. This vector field can be a result of a million forces acting. Okay, don't care. You don't have to individually understand those forces at all. See, Newton would have killed you at this point, because see, this vector field would have been the result of God knows what. And in Newtonian physics, you have to calculate even all those forces, even constraint forces, right? See, guys, understand this. When I say force, you have to be very clear about this. You all know centripetal forces. So, for example, you have a center. I put a ball, and the ball is angular momentum. You're kind of doing it like this. So there is what we call the centrifugal force, and then centripetal force. All of you would have read this. The centrifugal force is trying to make the ball fly off the angular momentum. It's going to fly off. Whereas centripetal force is trying to. Most of it is wrong, unfortunately. Okay. No. The whole point is centrifugal force is not a real force actually. It's a constraint force. Meaning, see, what happens is
with the mass of the
object and some angular momentum.
Yeah.
Whatever is the angular momentum omega of that thing, you calculate it, right? See the real problem here is this, and this is where Newtonian physics becomes tricky. Because what is the problem here? You have tied a string here, right? And you are rotating it. Now, the string has some tension in it. The string has some tension. If you rotate it fast enough, the string will break and it will fly off. And it will fly off. But under the condition it is not flying off, now Newtonian mechanics tells you that forces have to balance out. Otherwise, why is it not flying out? It has to fly out because this is a real tension. The centripetal force is a real tension in the wire. Okay, it is a property of the wire that you have used. It's got nothing to do with anything else. Now to balance it, you have to make up an imaginary force. Because this constraint force actually doesn't exist in nature. It only exists to balance out the constraint force of the wire. But in Newtonian mechanics, you are forced to put this on. Because without that, you can't explain this phenomenon. Why is it holding? You have to say, and then you will have stupid questions like, what is the maximum speed I can rotate at which it will fly away? Elasticity of the thing you put, and then of course they will say friction less, elasticity less, whatever nonsense question they'll give you, because if you put all of that, it becomes 100 times more difficult and unsolvable problem. Here you don't have to worry about it. You just have to say this is the vector field. That's it, the Hamiltonian. I don't care. I don't have to make up stupid forces like centrifugal force or whatever force and whatever. In fact, in general theory of relativity, Newton, which at some other point I'll talk about, I don't want to get into this. It's not a physics class, but gravity itself can be seen as not a force, but that's a different story. We will talk about it sometime else. So this is what it is. So, right? This is the Hamiltonian. Now, if you remember my previous diagram, these forces were upwards. In Hamiltonian, it is defined like this. This is the definition of an Hamiltonian. So if you want to get it to our case, you have to rotate it to 90 degrees.
Yeah.
Do this, no? Then it becomes a force field I drew. Then these become all of this move. All of this move.
But again, even that is not. We need not consider because the movement will be tangential.
Tangential, so you have to do that. So that is why if you rotate this, if you rotate 90 degree, if you rotate this 90 degree, what you call the gradient of h, because this is nothing but the gradient of h, right? Each one is a gradient. So you've rotated gradient because this is how h is defined. So now you rotate gradient of h 90 degrees. What do you get? You get nothing but h by p, and you get minus. becomes negative. This comes this side. So the slope is negative, right? See, what is positive slope? What is negative slope? If you have a curve like this, at this point, what is the slope? Is the slope positive or negative?
Positive.
Save yourself. This is negative. So yes. So that's why on hx it becomes negative. Don't get confused on things like this. Yeah, it's a slope of a gradient. Okay, slope of a gradient is fine. This is the equation. So s of x equals this. So if you rotate gradient of h by 90 degrees, which is nothing but equals to s, is equal to, which is the equation I wrote. Open plots. Nonsense. So now we will kind of derive this a little mathematically. Maybe 10-15 minutes will take. Okay, we'll derive this and then we'll talk a little bit more about how we will use it. But this part is clear, right? It's not very difficult. So the Hamiltonian is just defined like this, boss, nothing else. See, if you read a lot of books and a lot of videos, they will confuse the hell out of you on Hamiltonian. Hamiltonian will be seen as something very, 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 very complex that people can't understand. But I am telling you, it is very simple. It is just the surface field, okay, in a phase space at some energy level. That's it. That is all that a Hamiltonian is, nothing more than that. Okay, the rest of it is mathematical trickery that we will do here and there and there and there. Yeah, and there are a few important concepts that we still need to get to, but we will get there. Okay, it's not very difficult. We'll quickly get to some of those concepts. After this, study the Hermitian matrix so that next time I can start directly with quantum mechanics. I don't want to again spend time on this. From now on, it will be just in time. As I'm teaching quantum mechanics, if there's a topic that is not there and you don't understand, I will quickly explain it. Instead of, otherwise the introductory class itself will not end. So, people okay with that approach, right? That's what I'm going to do now. I'm going to get into quantum mechanics, and whenever you don't understand, whenever I have to bring up something, I can't also remember every single thing. Maybe there is something that comes up that I haven't spoken. If I have not spoken, right then we'll take 10 minutes and discuss that. So now let me write some of these things. Okay, this is just a recap now. If you do a recap, what is it that you have found? You have found derivative of x of t, comma p of t by dt. If you kind of say equals the surface field is what you're saying. This is the first one. So this is how the particle moves. From this, you will derive the uncertainty principle. So the tangent of the trajectory in phase space is equal to s. That's it. Same thing that I do. From this, it is very simple that if you want to do this, if you want to get to the next one, which is simply you can get x of t plus this whole thing you can write at sx. Because that's the definition. Right? Because this is how it moves. This is how it moves on this. So basically is this. So what does this tell you? If you know the initial, you can keep doing your dt again and again and again and again and get to the end. Similarly with p also. Again, quantum mechanics disturbs all of this. But at least you should first know what it is so that we can disturb it. Quantum mechanics, you will disturb all of this, right? Quantum mechanics does not actually follow this. Same rule. So it's in the red. Now we will get to a very, very important property. Okay, this is all very simple. There is nothing, just a recap. Just told you about Hamiltonian. This is nothing but here now I will write an equation that is important. At least the equation is not that important, but conceptually it's very important because we'll keep going here. So if you look at the trajectory, it is nothing but rotation 90 degree or the gradient of h, right? This is the same figure. So now, what is divergence of x? S. If I say divergence of S. So if you simply differentiate, right? If you simply differentiate that, it becomes what? By dx, because that's what dh by dp is. This is the most important result that you should remember. We will not be deriving this. They require some trickery to derive this. Okay, I think you can read any standard textbook to derive this if you calculate this, but it will take some time. It's about a page and a half of proof, but this is the most important result. It basically means in the phase space, as the particle is moving on a trajectory tangential to the force applied, the divergence of that path is zero. What that essentially means is, it's actually called a I don't know if you guys have heard the solenoidal. It's called solenoidal curve. What does a solenoidal curve means? That means as you across time, as this evolves, there is no discontinuity. It is basically a continuous movement, so that there is no imperfection. There is nothing like more force is getting concentrated at one point or more or less forces. It is the same force and it moves tangentially. So this is an important property of the Hamiltonian. Given the energy level, what do we mean? Given the energy level is constant, if the energy level is constant, in a phase space, the particle moves through a solenoidal space where the divergence is equal to zero. Divergence is equal to zero, hence curl also will be equal to zero. And this is very, very important. Also, you can think about it like this. If this is the area, these are equivalent. We don't have to prove it right now. If this is the curve that it is moving, then across time dt, the area of this curve is preserved. The area of the curve will be preserved. That's an important result. Okay, it follows from divergence equals zero. It follows from the same thing. Okay, but the area of this curve will be zero. This is again an important result because as you probably know, hydrogen atom, one electron, it has got multiple energy levels that it flows in. So each one of these can be taken as an Hamiltonian. That's why it's important in quantum mechanics. Each one of them is a Hamiltonian. And the reason what we are saying is, within the same energy level, how much ever time it rotates, the area remains constant. It does not suddenly become bigger or smaller or anything. It only happens when it gets to an excited state or another excited state. Only then it changes. That is why this is important. Okay, and this sort of curve is called a solenoidal curve, which is a word that we will use in quantum mechanics. It will say the curve is solenoidal. Essentially, what it means is the divergence is equal to zero, and this is a very important equation. Like the Lagrangian equations I gave, this is an important equation for the Hamiltonian. Okay, the derivative of the path with respect to x and p will be equal to zero. Okay, assuming this is in a phase space of x and p. Energy is constant at that level within that Hamiltonian. That's what on this curve only we are talking about. If from here you jump to the next curve, then it is not true. It is a different. From then something happens here and it moves to the next curve. then it's a different story. I'm saying on this surface, it is true. And this is actually a three-dimensional thing, but that's okay. We can visualize in two-dimensional, but actually it's a three-dimensional thing, right? The thing is three-dimensional. It's not really two-dimensional. That's why it's a surface. So I think this should be enough on Hamiltonian for today. Okay. So guys, I think somebody else left. Whoever is there, Dheeraj, some understanding?
Yes, sir. Getting it.
Yeah, I think I would recommend study this a little bit because it's a little bit complex, but don't worry too much about it. As long as you remember the divergence is equal to 0. Hence the curl equals to 0 on a surface area within the phase space. When I say within the space, it means at the same energy level. Otherwise, it doesn't mean anything. Okay, the energy level, whatever the k equals k0 or k1. So this is the basic understanding of Hamiltonian. So even in that big thing in Schrodinger equation that we said is a Hamiltonian, that whole thing is explaining the travel of this surface. Is what that entire equation is representing, and that is why we are able to substitute with one word, calling it the Hamiltonian of the photon or the Hamiltonian of the electron. We will see later when we are doing quantum mechanics how to derive that as the Hamiltonian, but that's fine. Okay, but at least in the classical field, understand this. This is used a lot in electromagnetism. Maxwell's equations and things like that you will use a lot everywhere. See, Maxwell's equations are also linear, by the way. That's something you can check. All the 4 equations that I gave you satisfy both conditions. Curl and divergence are also linear operators. So, divergence of V is equal to alpha divergence alpha V equals alpha divergence of V. Okay, and similarly the other one. So, both those properties, divergence and curl, will also satisfy. They are both linear operators. Okay, they are both linear operators. See, in Newtonian mechanics, why is it not linear? It's a very simple thing, right? It's m d2x by dx square equals force, which is equal to some v of t dt. Right? You're basically potential, or ddt of whatever, or you can write it in any other way. But it's the first derivative with respect to time. Okay, if you understand. The problem this is not linear is, if you want to write it as LU, then you have to bring this in equals to 0 and all of that. See, this can be any function. The potential need not be a linear function. The potential can be any horrible function. Can be x to the power 10 or x to the power cube or x to the power 4. So if you first derivative also will be 4x square or something. So it will not be linear. So the whole problem with Newton's equations is this force can be linear sometimes, cannot be linear sometimes. You cannot guarantee this to be linear because that is not a linear operator. I think that is why Newtonian mechanics is actually harder in some way. And it's not like linear is easier and non-linear is harder. That is another nonsense. Okay, but that's just something to keep in mind as we get into quantum mechanics, which I will get into some detail.